Hello everyone, my name is Oscar Fernando Randon Vargas and I'm going to talk to you about this paper that is called Learning the Depths of Moving People by Watching Frozen People. So what's different here? What's the challenge inside this paper? The paper, what it's trying to do is trying to compute the depths of moving people in videos by understanding and computing videos from handheld cameras doing mannequin challenges. These videos give a stereo representation of the scene while the camera is moving, but people are not moving. And also, moving targets in videos while the camera is also moving represent a challenge while trying to comprehend the 3D representation of objects. So what's different here is that this paper, although there has been a lot of approaches to trying to capture or compute the depth of certain people or objects inside a scene, is that the data set that they're taking to train the neural network comes from YouTube challenges. That is the mannequin challenges that was popular some time ago, where the camera was moving but the people were not moving. So this is kind of another opportunity for us. Mannequin challenges provide a good opportunity to have the necessary type of camera movement and static objects for a set of training videos for a neural network. So how do we do this? First, we have to condition the data set to train the neural network before we do any kind of computation. So we estimate the camera poses and depth using two types of methods. One called structure from motion and multi-view stereo, which will be used later on the same on this presentation. Of course, there has been a lot of related work on this. One of them is learning-based depth prediction, which assumes known camera poses and tries to predict camera poses along with the depth. This differs with current work in this paper because this paper will try to know or compute the depth of dynamic objects, unlike this learning-based depth prediction. We also have the depth estimation for dynamic scenes, which in general tries to predict the depth using various methods, but fail when it tries to predict the artificial and dynamic movement of people. For example, Constantinus tries to predict the depth of soccer players from FIFA video games, but this may work on these specific videos, but not for people in the wild. RGBD data for learning depth also it mainly focuses on the supervision learning on these neural networks, but only for indoor scenes. So when you try to give it a video of people outdoors, it fails to learn from it. And finally, the human shape and pose prediction tries to recreate a 3D human mesh from a single RGB image. And it's kind of impressive to do that, but what happens is that it relies only on the model of the human body. It doesn't take into account hair, clothing, and non-human parts of the scene. And finally, these methods rely on correctly detecting human key points, requiring most of the body to be within frame. So it's kind of hard for them to predict the depth of objects, such as tables or even just a part of a human, like a feet or a hand, if it doesn't represent the whole person. So where do we get the data set? This is the Mannequin Challenge dataset. The Mannequin Challenge is a popular video trend in which people freeze in place, often in an interesting pose, while the camera operator moves around the scene filming them. So we have a 12,000 candidate videos. So we have to create or at least try to predict an error that for which we have to filter the frames within the video. So here we have a formula to predict this error. Um, First, we estimate the camera poses and compute the dense depth with MBS, which I explained before, and then we apply the depth filtering mechanism. How do we get this error for these frames? First, we gotta do the depth with MBS for this technique, and then we subtract something called the depth map using the two-frame motion parallax technique on this two consecutive frames, and we applied an absolute on this, and then we're normalized by dividing by the sum of the depth using MVS and plus the depth from the motion parallax. So on the last slide, we rely on the MVS and motion parallax technique to filter those frames that are too different from one another. That means that there's not going to be any useful data to try to estimate the depth if any of those techniques cannot estimate anything. That means that if the two frames are way different from one another, then there's no point in trying to fit these frames into the neural network. So after that's done, then we gotta do filtering on the clips themselves. There are some things to consider when filtering the clips. If the clip at some point the people start unfreezing, then there's not gonna be much use for us on that video. If the synthetic graphical elements in the background, this can be like different moving objects in the background. This is gonna mess up the depth estimates. So we gotta filter those as well. We gotta remove the frames where the less than 20% of the pixels have valid MBS depth after two pass clean stage, and remove the frames where the estimate radial distortion coefficient is more than 0.1. This is for fish islands. That's gonna also be a problem when trying to estimate the depth. So what we obtained is 4,069 sequences obtained with a total of more than 170,000 valid image depth pairs, and we split our MC dataset into training, validation, and testing sets. This is going to go as an input for the neural network to train it. So what's going to be the input for our neural network after we have trained it? The full input into to our network includes a reference image, which is IR here, a variant mask of the human regions M, a depth map estimated for a motion parallax with human regions removed because we already have this in M, and this is going to be called DPP, and a confidence map C. This is going to boost our the performance in the prediction, and an optional human key point map called K. So this is the first step in the neural network. First, we're gonna have the depth from motion parallax. Motion parallax between two frames in a video provides our initial depth estimate for the static regions of the scene. This is having an image source and an image related to that, and we feed it to FlowNet 2.0, and we have as a product we have this, which are the initial estimates of depth and region detecting on the. One important thing that's gonna be used as input for the neural network is the confidence map. Our data consists of challenging internet video clips with camera motion blur, shadows, low lighting, and reflections. In such cases, optical flow is often noisy, compounding uncertainty in the input depth map, which is called DPP. The confidence map, it's called C, and here we have the a small formula how the confidence is measured. in which CLR measures the left-right consistency between the forward and backward flow fields, and the term CEP measures how well the flow field complies with the epipolar constraint between the views. And finally, CPA assigns low confidence to pixels for which the parallax between the views is small. Low confidence regions, which you can see here in the dark circles, in the first row, indicate the vicinity of the camera epipole, where depth from parallax is unreliable and it's removed. That means the pixels don't move as well when the camera is moving. So these dark circles are not reliable, so we have to remove them from the scene. So we're gonna have some losses. We train our network to regress to depth maps computed by our data pipeline. We need to scale those depth values since they differ from different input frames. Scaling variant and MSE square log space difference in depth between 2 pixels in the prediction and the same 2 pixels in the ground truth average over all pairs of valid pixels. The difference between the predicted log depth derivatives in x and y directions and the ground truth log depth derivatives at multiple scales. This is the formula we're gonna have to use for the loss in depth data that we have in the neural. We also have to do some kind of interpolation and smoothing for the depth in the pixels where no texture and also where the MVS method fails to recover depth. So what are the results? Here have we the qualitative results on the MC test set. The first row is the input for the neural network. The second row is the first approximation on the MVS approximation for depth. And then after the smoothing, I talked earlier, we have the third and the fourth row. In the third row, we can see the result of given as input the first line of frames, and that's it. We're not given as a parameter the confidence map, the depth, the errors, the losses. We're not given anything. The neural network is just working with the frame, the single frame from the top. And below we can see when we give everything to the neural network. That is the frame, the initial frame, the confidence map, the error variation, and all those things we talked about at the earlier slides. And here are the qualitative comparisons on the TUEM RGB dataset. So what's different from the other slide is that here we have 2 frames. We're not just we're not passing just one frame. It's 2. One, it's the image reference and the image source. Here we can see this is the first approximation, the GT, and there are some others that like the Dorn technique that as we can see, for example, here on the third line, fourth row, that is not quite estimating as well. It gets confused on these parts. And here we have something called the demon technique also that is cited in the paper, which is working a lot better, but still is missing some key points. And then we have which is the from this paper, this technique, where we input just the frame after we train the neural network with all the mannequin challenges videos. And then finally, this has the best performance. This is the full one, which means we're passing these 2 frames, the confidence map, the loss correction, and all those parameters we talked earlier. So this works as well. For example, here between this one and this one, we can see that the table is not getting as predicted as well. And here it's doing just fine because this part of the table it's closer to the camera, so it's predicting the depth very well. And also we have the all the people edges that are working correctly. So all in all, it's working better than all the other ones. Maybe the demon it's working kind of better than the Dorn, but the the technique on this paper it's working a lot better. So this evaluation it's kind of the same, but it's the people are performing complex actions here and captured from different camera poses. So it's kind of harder than the other slide for the techniques to work. And also we can see here that it's working a lot better for this paper's technique than other like Demon, Chen, or Dorn. So in conclusion, we demonstrated the power of learning-based approach for predicting dense depth of dynamic scenes where monocular camera and people are freely moving. Also, it's kind of interesting because the datasets can come from unexpected source. In this particular case, from YouTube videos challenges that it's not that common to have a lot of videos and dataset for this kind of predictions without having a lot of samples of camera movement and freezing objects, and even less so for people that are frozen. And also the predicted depth may be inaccurate for non-human moving regions such as cars and shadows. This is a known challenge for this paper. It may not work so well for this type of objects, but it works pretty well for humans. And that's it for my part. Thanks a lot for listening.